This video is on using properties of logs and how to help in simplifying logarithms and solving exponential equations. This first part of it I want to discuss is the properties of logarithms. And if you're in my course, you would have this provided to you as a handout, just so you don't have to write it all down. We'll go over the properties and then we will do some examples using them. So for these properties of logarithms, first off, the first one here, it says log base a of m times n. So if you have multiplication inside of the log as the argument, what it's really telling you is that's equivalent to taking the log base a of the first factor plus log base a of the second factor. So when you have multiplication inside of a log, you can write it as addition of each log individually. Remember, the base a here is a number a greater than 0. A doesn't equal 1. But we're just using a just to keep it as a general base. But the bases have to match. You can't do this if the bases are different. The second rule says that if you have division inside of a log, then you can take the log of the numerator and subtract it by the log of the denominator. Again, making sure the base stays the same as the original base. The third rule, says log base a of m to the k power. So it's really saying if your argument is being raised to a power, what you're allowed to do is you're actually allowed to bring that power down to the front, is really what this rule is showing us. So you bring the power down to the front, and that's equivalent to k times the log base a of m. The fourth rule here, log base a of a, if you're not sure how to get that, remember what a log means. It means a to what power gives me whatever the argument is. Well, a to what power is going to give me a? Well, a to the first power gives me a, because the log is equal to the exponent on the base to get the argument. So if you have log base a of whatever the argument is, those match, it's going to be 1, because a to the first power gives me a. This rule here, the fifth rule, log base a of 1, it's really saying a to what power gives me 1. Well, a to the 0 power is what gives me 1. So log base a of 1 equals 0. So log of any base of 1, is always going to be equal to 0. We take the log of 1, no matter what the base. The sixth rule here, we got log base a of a to the k power. So the argument is just the same base as the log, The exponential is the same base as the log. If the bases match, you can just take the exponent. The reason being is it's saying a to what power gives me a to the k. Well, that power has to be k to get a to the k, so it's just equal to k. So if the bases match, you just take the exponent. And then the last rule here, the seventh rule, really has to do with the change of base formula. Suppose I had log base b of m, and I wanted to get that, using log base a to evaluate it. You really take log base a of the argument over log base a of the base. And most frequently, you're going to see this change of base formula, So this is really what we call change of base formula. And most often you'll see it using the buttons that you can use for logs on your calculators, which is log base 10 or log base e. So another way you might want to write this, if I have log base b of m, it's equal to, you could take the log log, which means base 10 of the argument, over the log base 10 of the base b. Or if you wanted to do it with natural log, this is equal to, you could take natural log of m over natural log of the base b. So these will come out to the equivalent values, but make sure that you realize that if you're using log base 10 here, it has to be log base 10 here. If you're using log base e here, it has to be log base e here. So natural log is log base e, log is log base 10, any other log with any other base is just whatever the base is. But this is the same rule I wrote above, except for I'm being very specific about what a is. In this case, a is base 10. In this case, a would be base e. Let's take a look at some examples using these rules. So, for example, if I said we are given, so we're telling you this part. So given log base a of 4 equals 0.23, and log base a of 5 equals 0.76, we're going to use the log rules to help us find very specific calculations. So if it says find, and then we'll do a few of these. So if I said to find the first one, log base A of 20. Well, what you should recognize here is that I have to use log base A of 4 and log base A of 5 to make it, look like log base A of 20 in order to get these values. So what equivalent form could I write log base A of 20 in to use log base A of 4 or log base A of 5 or both to calculate what I need? So when you're looking at this log base A of 20, something you should notice is 20 is actually 4 times 5. So the first thing I would do is rewrite this as a product, right? Log base A of 4 times 5 is the same as log base A of 20. And then we can use the rule that we had about, right, if we have a product with multiplication inside the logs, how do I rewrite it? Well, I can rewrite that using the first rule as addition of the logs individually. So I can rewrite this as this equals log base A of 4 plus log base A of 5. And you put parentheses around that or not for the argument. They mean the same thing. But then once you're here, now I can substitute in. I know what log base A of 4 is, and I know what log base A of 5 is, right? So log base A of 4 would be 0.23 plus log base A of 5 is plus 0.76. And then if you add those together, you'll get 0.99. So log base A of 20 would be 0.99 based off of what they were given to us. The next one here, if I say log base A of 4/5, well, this is division inside of the log, and remember our rule says if we have division inside the log, we could write it as subtraction, or the difference of the logs, taking the log of the numerator minus the log of the denominator. So I'm going to rewrite this as log base A of 4 minus log base A of 5. Again, you wanted to get it into a form where you had log base A of 4 and log base A of 5 because that's when you can use this. It's not take the log of the numerator over the log of the denominator. That is not how this works. That's not equivalent. So when we're looking at this log base A of 4, substituting in for this first part, I have 0.23 minus log base A of 5. We know it's 0.76. And if we do that subtraction, we get negative 0.53. So log base A of 4/5 would be negative 0.53. Let's look at this one. If I said log base A of 125. Now remember, the first part of this, our goal is to write this as some sort of, multiplication or power of 4 or 5, so I can use one of these identities they gave us at the top. So when I see log base A of 125, I know 125 is the same as 5 to the third power. So I'm going to write this as log base A of 5 to the third power. It means the same thing as log base A of 125, right? 5 to the third power is 125. And then what does my rule tell me? Well, if I'm taking the log of something with the argument being raised to a power, that tells me I can bring the power out in front. So I'm going to bring this 3 down in front and I end up with 3 log base A of 5. Now that I've isolated this log base A of 5, you couldn't just sub 3 in, or the 0.76 in here and make it 0.76 to the third power because it's not log base A of 5 yet. Now it is. We have 3 times that, so this is equal to 3 times log base A of 5, which is 0.76. And then evaluating that, 3 times 0.76 gives us 2.28. What if I gave you this one? We said log base A of 1/4. Initially, you can see that you have division inside of the log as the argument. So if we have division inside the log, we can take the log of the numerator minus the log of the denominator. So I'm going to take this as log base A of 1 minus log base a of 4. And so I have the log base a of 4, which I was saying I needed from above. I don't have any log base a of 5, and that's okay. You don't necessarily need to use both. But log base a of 1, make sure you know how to evaluate that. Even though I didn't give it to us, remember what we said. When you take the log of 1, no matter what the base is, right? Log base a of 1, no matter what the base of log is, if you're taking the log of 1, it's always equal to 0. Because it's really saying a to what power gives me 1. Well, that's a to the 0 power. So this part we know is going to be 0. So it's just equal to 0 minus log base a of 4 now. We know that from above is 0.23. So the answer here is negative 0.23. Let's look at a couple more. If I wrote this, so call this example E, if I had log base a of the square root of a, the first thing you should notice is that, you have the square root of a in here, and we can change a square root into an exponent. All right, we know how to write roots as exponents, so this is log base a of a to the square root would be to the 1/2 power. And then, we know a rule that if I have log base a of a to a power, then this is going to, a to what power gives me a to the 1/2? Well, the answer is just 1/2, and you could do that right away. That's coming from our rule that says, right, log base a of a to the k is just equal to k. So if the bases match, right, so if your argument's an exponential and you have a log of the same base, you can just take the exponent as the answer. It's saying a to what power gives me a to the 1/2. The power has to be 1/2. If you did use the exponent rule where you brought the 1/2 in front, you'd have 1/2 in front, you'd have log base a of a, and log base a of a would be 1, and it'd be 1/2 times 1. You would actually get the same answer. So understanding both ways of looking at that is somewhat important. And if I wrote this, log base a of, say, 9. Well, you could write 9 as something involving 4 and 5, right? Because our goal is to try to get to this. But if I try to write log base a of 9 as something involving 4 and 5, the only way I really would do that is log base a of 4 plus 5. But none of our rules allow us to separate addition or subtraction inside of a log. And that's actually something important to know. You actually, if you have addition or subtraction inside of a log, you can't separate that into individual logs. Right? So our rules don't say anything about if we had adding or subtracting inside of a log. You can't turn this into log a of 4 plus log a of 5. Right? That's what the original one was. That was log base a of 20. So you really can't use any of the rules here. This doesn't simplify. So in this case, it's impossible to evaluate. All right, so impossible to evaluate with the information given, because we don't know enough to do it. We can't make this a log base a of 4 and a log base a of 5. So it's important to know how to use those log rules to help you in simplifying. We'll take a look at a few examples now where we actually solve equations and logs help us there. So let's say for these examples we'll say solve. And when I say to solve these, mostly they'll start out as exponentials, and we're going to use logs to help us solve them. So if I have e to the t equals 35. One way of solving this, if you didn't know the log rules, would be just to rewrite it as a log, right? Because you're trying to get that, you're trying to solve for t, you're trying to get that out of the exponent. But if you know the log rules, you might notice that, okay, this is log base e. In an earlier video, we talked about how, natural log and log and the exponential base e are going to be inverses. So if I take the natural log of e to the t, I have to do it to each side. So I'm really taking the log of each side here, and I take the natural log of 35. So this is what we're doing. Take the natural log of each side. Now the reason we do this is that, well, natural log of e to the t, remember the bases match. The base here is e, the base here is e, so natural log of e to the t is just going to be t. It's using our rule where if the bases are the same, you can just take the exponent. If you didn't use that rule and you brought the t down in front, natural log of e would be 1, and t times 1 would still give you 2. So at t equals natural log of 35. Now this is the exact answer. So you've solved it if you get this, right? This is the exact answer. All right, so this answer is exact. I'll write that a little more neatly. So that's the exact answer. Now, if I asked you to approximate this, you would use your calculator to do it. On your calculator, if I want to take the natural log of 35, if you have one that displays everything on the screen like this one, you can just put natural log 35, close the parentheses, hit enter on that, and it'll give you a number. So we see 3.555348061. It's all an approximation. This number will go on forever. It's irrational. But we'll approximate the 2 decimal places here. Only do an approximation. So in this case, I have 3.5. The 5 will round that second 5 up to a 6. So t is approximately 3.56. I only want you to do an approximation, though, if I ask for an approximation or if it's an applied problem. All right, so for this approximation, it's giving you what natural log of 35 is almost equal to, but the exact value is leaving it as natural log of 35. Sometimes people, when they see leaving an exact form, they try to make a decimal, and that's actually the opposite of what you'd want to do. You want to keep it as a natural log of 35. What this tells us is that, remember, when you're solving, it's saying e to what power gives me 35? Well, e to the natural log of 35 will give us 35. But if you were to try and see if this works out nicely, you could check it on your calculator. We won't do this for all of them, but you could say, okay, e to the 3.56 power, let's see what that comes out to. And you see it comes out to 35.163, which, is pretty close to 35. So we probably have the right answer. As we round this, we're losing some of our precision on how close to 35 you will be. The more decimals you use, the closer you'll be to 35. The exact value, though, is natural log of 35. Let's take a look at another one. If I said this one, if I said we're trying to solve e to the 4t equals 1600. In solving this, the first thing you should notice is that you have an exponential trying to solve for t, trying to get that exponent out of there. I, again, would take the natural log of each side. So natural log of e to the 4t is equal to the natural log of 1600. And on the left side, natural log of e to the 4t, remember, natural log of e to a power is just going to be the power, because remember, the bases match, so you're just going to get the exponent. So natural log of e to a power just gives you that power, 4t, equals natural log of 1600. We'll keep that there. You don't really need the parentheses if you understand that natural log has an argument always. Right, so it's a natural log of 1600 because it's a function. And then, how do we solve for t? Well, I want to divide this by 4, and I divide by 4. So you have t equals natural log of 1600 all over 4. Now the question here is, can I simplify this? Can I cancel that 1600 and that 4? And the answer is no, because remember, this is natural log of 1600. This is part of the function, so it's not multiplication. It's natural log of 1600 divided by 4. That's actually your exact answer. All right, so that's your exact answer. If you wanted to do an approximation with the decimal, right, t is approximately, if I was looking at this on your calculator, natural log of 1600, close the parenthesis, divide by 4, make sure you close that parenthesis or it won't come out the same. You get approximately 1.844, so we'll say 1.84 rounding it down. Remember, this is the approximation. When we solve these, have an understanding that we're isolating the exponential in order to use the log on this. If this exponential wasn't isolated and there was a value in front, you actually would have to isolate the exponential first. And these ones I've given them to you isolated, but they won't always be that way. Let's take a look at another one. So if I said, I'll call this letter C, if I wanted to have 4e to the 7t equals 3. I'm going to solve that for t. In this case, the exponential is not isolated because we have a coefficient in front of 4. So the first thing we want to do to isolate the exponential is remove that coefficient. In this case, this means 4 times e to the 7t, so we're going to divide by 4 to each side. So you have e to the 7t equals, this will be 3/4. Leave it as 3/4. You could make it a decimal because it comes out exact, but in this case I would leave it. And then how do I get the t, right? How do I get this exponent out of the exponential? Well, the way we do it is we take the natural log of each side. So we have natural log of e to the 7t equals natural log of 3/4. This gives us 7t on the left side, because remember, natural log of e to a power is just the power, because the bases match, and that's equal to natural log of 3/4. And then we want to divide both sides by 7. So I divide by 7, divide by 7. I have t equals, now, natural log of 3/4 over 7. That's an answer. Don't let it throw you off. You can't get into this 3/4. The natural log of this is the function. So it's over 7, and that would be a solution. That's the exact solution. Right? If you wanted an approximation, just to practice approximating it, on your calculator you would want to type in natural log, so ln 3 divided by 4, close those parentheses, and then divide by 7. And you end up with a negative here, negative 0.04109, so we'll say negative 0.04, just to 2 decimal places. So negative 0.04 is my approximation. Remember, if I ask for exact, leave it exact. If I ask for an approximation, I'll tell you how many decimals. We've been using 2 just because that's what I chose to use. If your calculator does not have a display where it shows all the steps, you want to make sure you understand how to substitute this in. If you were doing it, you would take the 3/4 first, then, so do 3 divided by 4 equals, and then hit the natural log button, and then divide by 7. So essentially when you're working with the log, you type the inside first, then hit natural log, then do the other operations to it. We'll just take a look at one more here. If I had 3 to the t power equals 35. Well, first thing to look at here is that my base is 3. In all the previous problems I just showed you, the base was e. That doesn't really change what you would do. You could still take the natural log of each side. Now, this exponential is already isolated, which is good, right? Because otherwise you have to do what we did earlier. So we have natural log of 3 to the t power equals natural log of 35. That's me taking natural log of each side. Now, what you can't do is the bases don't match, so you can't say this just becomes t, because this is base e and this is base 3, so we can't use our rule that says if the bases match, take the exponent. What we can do, and why it's always helpful to take the log, is that I can bring the t down in front. Now, no one says that you have to use natural log here. You could use log of any base. We use natural log most of the time. We also have log base 10 we could use if we needed to. Those are the ones that are able to be evaluated on your calculator, and that's why we use those most often. But the log rule says if I have log of something being raised to a power, I can bring the power in front and then just keep the log as multiplication right after it. So it's t times natural log of 3 equals natural log of 35. And then I want to solve for t. Well, if this is t times natural log of 3, you want to divide by natural log of 3 and divide by natural log of 3. And these cancel. You end up with t equals, this is natural log of 35 over natural log of 3. So a couple things to point out. You can't cancel these natural logs here. Sometimes people do that and they just say 35 over 3. This isn't multiplication. Remember, it's not natural log times 35. It's natural log of 35. This isn't natural log times 3. It's natural log of 3. So these are functions. They have to stay as is. They aren't going to cancel out. And there's really nothing else you can do with this. You can't rewrite it as subtraction because it's not the log of something being divided. It's actually division of logs individually. So this is the exact answer. All right, so that's your exact solution. Now, if you want to approximate it, you could do ln of 35, so natural log 35, close the parenthesis, divided by natural log of 3, close the parenthesis. Hit enter on that, and we get, this is approximately, I got 3.236, so we'll say that's 3.24 as the approximation. Make sure that you're approximating only when asked, all right? Or if it's an applied problem, you don't want to just do approximations across the board. We expect the exact answer if we don't ask for an approximation. You may have approached this problem in a different way. If you saw this 3 to the t equals 35, and maybe you didn't think of taking logs. And it's okay if you didn't, although it's going to be easier for you to work with if you did most of the time. You could just say, let's rewrite this as a log, all right? So we're going to rewrite this as a log. If you remember how to rewrite as a log, all right, you want to start with saying log base, whatever the base is 3, of, the number that your exponential is equal to gives you the argument. So log base 3 of 35 is equal to, remember log's always equal to the exponent, so it's equal to t. And that's a solution. I mean, that's an answer. T is equal to log base 3 of 35. That means the same thing as that exponential. You solve for t and you have an exact answer. And you could say this is exact, right? So that's one way of expressing your answer. But keep in mind that if I'm looking at this change of base formula, right? If I was saying t equals, remember the change of base formula we talked about here, number 7? Change of base formula says you can take the log of the inside over the log of the base, right? That's what it really says. Or the natural log of the inside over the natural log of the base. So when I use my change of base formula, let's say I was using the one natural log. I could take natural log of the argument over natural log of the base, which in this case is 3. So you're getting the exact answer. It's just, this is written without the change of base formula. This actually produces the change of base formula when you're doing it. That's how you get the change of base formula. So these are equivalent. It also would be equivalent if you did your change of base formula and just used log of the argument over log of the inside. It's just using base 10. But these are equivalent values, and you could check that out, right? So we just got the natural log of 35 over natural log of 3. If I was to do the log base 10 of 35 divided by the log of 3, you see you get the same value, 3.2362, keeps going. These are equivalent, meaning when you do this part up here, you could use natural log, you could use log base 10, you could use log of any base, but you have to be consistent. You can't do one side with one type of log and the other side with a different type. The last thing we'll look at here is just some applications using the interest formula. And you probably are familiar with this from earlier, but this handout here talks about interest compounded n times per year, and then we'll talk about a new way of looking at it using exponentials. So it says for an investment or loan with interest compounded n times per year, the balance A after t years is calculated by the formula, and we have A equals P times, in parentheses, 1 plus R divided by N, all that part to the NT power, where A is the balance after t years, so it's the amount in the account after t years if left untouched. P is the principal, the initial amount you invested or borrowed. R is the compound interest rate. R is your interest rate as a decimal. Make sure you use it as a decimal. N is the number of times the interest is compounded per year, right? That's the N times per year we talked about here. And T is the number of years. So if I ask you to use this formula, right, it says if you invest $7,000 into an account ending 4% interest compounded quarterly, so they're telling you how often, how much will be in the account in 5 years? Well, because they're telling you how often, right, they're telling you how many times per year, we know we're using this formula above, right? And quarterly means N equals 4. So really I want to substitute in, right? It says how much money will be in the account in 5 years. So that's telling me I'm trying to find A. So substituting into my formula, I would have A equals the principal. Principal is the initial amount invested. You invested $7,000. Or, you could say the initial amount borrowed if it's a loan. So A equals 7,000. And then times, in parentheses, 1 plus R. What's R? Well, 4% interest tells you that R is equal to, remember, percents out of 100, so you move the decimal place 2 to the left, or you can say 4 divided by 100 is 0.04. So 0.04 over N, which is 4, raised to the NT power, well, n is 4 times t is number of years they told us right here, 5 years, so 4 times 5 power. And we're going to evaluate this. Right, so we have a equals, this is 7,000 times 1 plus 0.04 divided by 4 is just going to be 0.01. So this is 1.01 because 1 plus 0.01 is going to be 0.01 to the 4 times 5 is 20th power. And we'll evaluate this on our calculator. If you have a calculator that displays everything on the screen, you could type it in as you see it. If you have a calculator that doesn't display everything on the screen, you want to raise to the power first, follow your order of operations, and then multiply by the 7,000. So in doing this, let's see what we get. So 7,000 times, and then it's 1.01, that part raised to the 20th power. And we get, now the exact value, you know, we don't really see. The approximation here, it's money, so we want to round to 2 decimal places. So this is equal to 8,541 we got 330, so 0.33, and this is dollars, right? So $8,541.33 will be in your account if left untouched after 5 years with 4% interest compounded quarterly. Now, that's fine and good. You know, interest can be compounded, you know, quarterly, you know, it could be annually. If annually, n would be 1. You know, you might see different different terms in there. You could say, you know, semi-annually. It could just tell you compounded 6 times a year. Whatever it might be, make sure that you're using that in this formula here. Now, below this, we have if interest is compounded continuously. So interest is compounded over and over and over again on a continuing rate. So it's not at set time intervals. It's now, right? Interest compounded continuously. You know, it's a different formula, but it works in the same way. It's actually what happens is, as you take this formula above and take the limit, as n is going to infinity, as the number of times you calculate it goes forever, you get to this formula, which says if interest is compounded continuously, and this is the key part of this, is how you know to use this formula. If it says compounded continuously, the balance A after t years is calculated by the formula A equals PE to the RT power. Sometimes you'll remember it as PERT. Just make sure you know the RT is the power on E. A is the balance after t years, so it's the amount in the account after t years if it's untouched. P is the principal, which is the initial amount invested or borrowed, just like it was in the previous formula. R is the compound interest rate as a decimal, just like it was in the previous formula, and T is the time in years. So the only way you know you're using this formula is if the problem you're looking at actually says compounded continuously. That's when you're using this formula here. So let's take a look at a couple examples. It says if you invest $7,000 into an account earning 4% interest compounded continuously, how much money will be in the account in 5 years? Here it is, compounded continuously. That's telling me use A equals PE to the RT. And in some cases you might see P listed as A sub 0 as the initial amount, and we'll talk about that a little later, but A equals P to the RT, and they're looking for how much money will be in the account in 5 years, so we're trying to find A. So I know we have A equals, P is the principal, they said $7,000 is what you invest, so equals 7,000 times E. E is our, you know, irrational constant E. You don't sub in for E. E is a number. R is the interest rate, so 4%. R is equal to 0.04 as a decimal, moving that 2 places to the left, or you could just do 4 divided by 100 if you're not sure. So 0.04, and then times T. T is 5 years, so 0.04 times 5. And when you look at this, you know, we can simplify the exponent there. So we have A equals 7,000 e to the 0.04 times 5. I would do that part first before you do any calculations. 0.04 times 5 gives us 0.20 or 0.2. And then to evaluate this, if you have a calculator that displays everything on the screen, you can write it as you see it. So you could say 7,000 and then e, right? So times e to the 0.20, close that parenthesis, and you end up with the amount is, remember this is money, so I have 8,549.81, and the 9 after it rounds it up to a 2. Remember, 2 decimal places for money because that's our change, so it'd be 8,500 49.82, and this is in dollars. If your calculator did not display everything on the screen like I had, remember, follow your order of operations. Do e to the power first, then multiply that value by 7,000. You should get to the same place. So we have $8,549.82 in the account after 5 years. And it says compare this to your answer from the last example. And the reason I want to compare these is because, I gave you all the same information, the same principal, the same interest, and the same time. The only thing that was different was how it was compounded. And if you notice, compounded quarterly gave us $8,541.33. Compounded continuously gave us $8,549.82. So the question really is, what's better? If all other things are equal, well, you want your interest to be compounded continuously because you're going to be earning more money over time. In either of these cases, if I asked you how much interest did you earn, you would take the amount in the account, subtract off the principal, and then that would be the amount left over, would be how much interest you earned over that time. Let's take a look at one more. It says, if you invested $4,500 into an account earning 6% interest compounded continuously, that's important, how much money will be in the account after 8 years? So if I say compounded continuously, that's telling us to use our formula, A equals PE to the RT. And how much money will be in the account after 8 years means I'm looking for A. So we know A equals P, which is the principal. The principal is how much you invest, the $4,500. And then E, right, to the RT. R is 6%, so 0.06. Right, this is R as a decimal. Times T. T is how many years? 8 years. Now, if they didn't tell you this and they just asked you to find a function, they didn't tell you the years, we just put T here. And then A would be a function of T, and you could figure out how much would be in the account at any time T in the future. Here they told us it's 8 years, so we'll put times 8. And then we just want to evaluate this. So we end up with, this is 4,500 e to the 0.06 times 8. Make sure that you're doing that part first. So you get 0.48. So e to the 0.48 power. And then if your calculator displays everything on the screen, you can actually just multiply these in together now, just as you see it. If it doesn't display everything on the screen, e to the power first, then multiply by 4,500. So we have 4,500 times e to the 0.48 power. Hit enter on that, we get 72.334, so we're going to round that down to 0.33, because remember this is money, so 72.33 we said. And remember this is dollars, make sure you include the units. So after 8 years, that's how much money we would have in the account, $7,272.33 would be in your account after 8 years. If we change the time here, right, if we just left this as, write an expression or write a function determining how much will be in your account after t years, we would just call this t here, and we'll talk about that a little bit later. So hopefully this was a good refresher on how exponentials and logs work with one another. As we move on into the course, we'll talk about other applications.